Let's say you have a startup and decide to use a public cloud to deploy your applications. To deploy your first application, you create a security group, open a few ports, and provision EC2 instance. At this point, instead of adding more features to a single application, you embrace a microservice architecture and deploy a second application. At a minimum, you would need to open a new port between these two applications so that they can interact with each other. At this stage, you have two security groups and two EC2 instances in your AWS account. Once you've built a minimum viable product, you decide to invite paying customers. However, if you continue using a single environment for development, you might make mistakes and introduce bugs. At first, customers might tolerate this, especially if no one else offers similar features. However, as your business grows, you realize you need to test your features before deploying them to clients. Using AWS Console, you create a separate development environment with the same security groups and EC2 instances. Now, suppose you create another microservice and deploy it on its own EC2 instance in the development environment. After testing, you decide to promote it to production. But first, you must create a new security group and EC2 instance in the production environment as well. At this point, it's still manageable. Then a team member suggests decoupling your microservices using a messaging system like Kafka. This requires significant infrastructure changes, creating a new security group, closing ports on old groups where applications interacted directly, and opening ports for Kafka so applications can publish and consume messages. Then you must very carefully replicate these changes in the production environment. Additionally, decoupling your applications makes it more difficult to test them. For example, if one application changes the schema of a message it publishes to Kafka, all other applications must be updated. To solve this, you create a staging environment. In the development environment, you develop and test individual applications, while in staging, you test entire platform. As your business grows, you may need to create dedicated environments in the countries and regions where your customers are located. You could end up with 5, 10, or even more environments. Deploying a new application requires applying changes across all these environments, which is time-consuming and error-prone. At this point, managing existing infrastructure and creating new environments manually via AWS Console becomes increasingly challenging. Now, you start thinking about automation. The first thing you can do is to create a shell script. Instead of clicking buttons in the UI, you can capture the same steps as AWS CLI commands in the script. You can definitely replicate everything you do in AWS Console using a shell script, such as creating security groups, EC2 instances, and so forth. However, the problem with this approach is that while you can quickly provision and create new environments, it's not ideal for managing existing environments, often referred as second-day operations. The first day is when you create environment, and the second-day operations involve day-to-day management of that environment. For example, you can create EC2 instance using AWS CLI, but let's say a week later you decide to increase EC2 instance type to a larger one to support more traffic. You cannot simply rerun the same command and change the instance type. The first issue is that your shell script or AWS CLI has no way of knowing which EC2 instance to modify. It lacks memory or state to remember which EC2 instance the script created in the first place. The second issue is that you need a different script, or at least different commands to modify EC2 instance. You need to stop the EC2 instance, update the type, and then start it. Additionally, the script must know which EC2 instance to update, so you need to provide EC2 instance ID. Another problem is that when you have multiple team members, it's hard to tell who made the change and when. Now, you're thinking it would be great if instead of focusing on the commands we want to run to manage our infrastructure, also called imperative approach, we could just declare everything in one place and apply it. In this case, if you need to create EC2 instance, you add additional item to your configuration and run apply. If you need to modify existing EC2 instance, you update the same configuration file and run apply again. That's where Terraform comes from. Terraform is quite simple. You have configuration files that describe the desired state of your infrastructure, and Terraform performs necessary actions to achieve it. It has a state file where it keeps track of all components managed by it. And that's how Terraform, for example, remembers which EC2 instance it created. So we established that to manage infrastructure using Terraform, you need a configuration file. But how does Terraform know that I want to create a virtual machine in AWS and not GCP? Well, it uses resources with different types of infrastructure components. For example, to create a virtual machine in AWS, we would use AWS instance, and to create the same thing in GCP, we would use Google Compute instance. Initially, Terraform included all those different resources in its own source code. So every time a public cloud introduced a new managed service or simply added additional feature to existing one, they would need to make that change in the Terraform source code and release a new version. To make it more flexible, the logic specific to cloud providers was removed from the Terraform source code and extracted into their own modules, which are called Terraform providers. So now Terraform only has core logic on how to work with those resources, build dependency graphs, and register those components in the Terraform state. But the actual logic that can create EC2 instance in AWS and similar tasks is now located in its own providers. So let's say we still need to manage our three environments. We would still need to copy and paste exactly the same configuration files into different folders. Well, the problem is that when you change something in one environment, you would need to copy and paste the same thing over and over again. And in large companies, when you have 5, 10, or even more environments in different regions, copying and pasting seems like a bad practice that can lead to mistakes. To solve this problem, Terraform came up with modules. A module is just a folder with all Terraform configuration files responsible for a specific component, like networking, security, or even entire environment. Now, we can simply reference that folder from the Terraform configuration files and apply exactly the same infrastructure everywhere. Obviously, if you have different environments, something must be different in them. Maybe you use different regions, or most likely development and staging would be much smaller than the production environment. Maybe instead of 50 instances in production, you would have 10 in staging and 2 in development. Now, we need a way to customize each environment. And for that, we can use Terraform input variables. Also, it's common that one module, for example, would create a VPC and subnets, and another module would need that VPC ID or subnet ID to create EC2 instance. For that, Terraform has output variables. So variables are like function arguments, where a module is a function and output variable is a function's return value. This way, we can dynamically retrieve a VPC ID from the output of one module and use it as input variable in another module. However, if you have many different environments and make a change in a module that is used by all the environments, it will trigger immediate update of all environments, including production. This is not what you want. You want to gradually release and test that infrastructure change one environment at a time. For that, we can create a Git repository for each module and use Git tags to reference a specific version of that module. Now, by using tags, we can gradually roll out that new version to all environments. Now, let's say you are the single person who manages infrastructure. When you create EC2 instance using configuration file, it provisions EC2 instance in AWS and registers it in a local JSON file called Terraform State. The problem is that if you have another team member who might want to create another EC2 instance, he or she would use your configuration file and add another EC2 instance. So when that person runs Terraform, it would create not one but two EC2 instances, because the Terraform state is only located locally with the person who initially created that EC2 instance. The first step to solve this would be to commit Terraform state along with the configuration files to Git and require anyone who wants to make any changes to pull the Git repository first every time. This might work if your team member is in another time zone and you work at different times. But what if you try to make changes at the same time? One of you might get outdated state, which could lead to problems. Or someone might simply forget to pull the Terraform state. To avoid this, Terraform can store that JSON state file in a remote location like S3 bucket. So now, every time you run Terraform, it will automatically pull up-to-date Terraform state from that location and use it to create a Terraform plan with required changes. But we still have a potential problem. We want to avoid race conditions and prevent any two people from running Terraform at exactly the same time. Terraform can obtain a log using DynamoDB in AWS, for example, which would block anyone else from running Terraform. This is the main idea behind Terraform, and the rest of it we'll cover during hands-on tutorials. First, we need to install Terraform. Follow the steps on this page for your operating system. It's very straightforward. On Mac, for example, I can use Homebrew Package Manager. First, I add Terraform repository. Then install it using brew install. And most package managers will also keep Terraform up to date. Next, verify that Terraform installed successfully and make sure you have a version higher than 1.0. We also need to install AWS CLI. If you don't already have it, you can use a package manager to install it as well. We'll use it to create AWS profiles and in later sections to authenticate with EKS clusters. Now, let's start on Terraform initial folder structure. I use numbers as prefixes in folders and files. It's just for you to make it easier to follow. Terraform does not care about file names at all. They just have to have .tf extensions. First of all, we need to declare a provider that we'll use in this tutorial. Providers are specific modules that combine resources for a specific cloud, like AWS in our case, or a specific tool, like kubectl. For AWS provider, we at least need to provide a region. Then, optionally but highly recommended, define some version constraints for Terraform and all the providers. It's especially important when we start to create Terraform modules. Next, let's go ahead and search for Terraform AWS VPC on Google. Terraform has resources that are used to manage objects in AWS in this case, and it also has data sources that are used to dynamically retrieve information from the cloud. You can scroll all the way down to the data section. Alright, let's select AWS VPC and take a look at how we can use it in our Terraform code. As you can see, it does not create a VPC. Instead, it provides details of the existing VPC, such as seeder block and other stuff. So in order to define it in the code, we only need to provide a VPC ID. Let's find it in AWS console. For this tutorial, we need to have a default VPC in our region. So please make sure that you have it or just create it temporary. Let's go ahead and copy VPC ID and paste it into Terraform code. Also, Terraform has output variables that are useful when you want to share certain details from one Terraform component to another, especially useful in Terraform modules. Right now, we just want to expose a VPC ID as output variable and print it to the console. It has a value parameter that you want to set using a data source. It's going to be a data keyword first, then the type of the resource, which is AWS VPC, then the variable associated with it, in this case main. In Terraform modules, we frequently use this keyword for the variable if you only have a single instance of the resource in our code. And finally, we need to know what attributes AWS VPC resource exposes. The best way is to go back to the official docs and scroll down to the attribute reference section. So here we can find all the variables that we can use, such as a seeder block. So to summarize, we're not creating anything in AWS. We just dynamically retrieve all the details of the existing VPC in our account by VPC ID and return seeder block. Now, let's switch to Terraform and initialize the project. It will download AWS provider to the local folder and create a log file with all the dependencies, as JavaScript or Golang does with a summary file. So we have a log file, and we also have provider itself. Make sure to commit the log file to the Git and add .terraform folder to the gitignore file. Now we can try to run Terraform plan. If you have never used AWS CLI before, it will fail with a permission denied error, but most of the time when you decide to use Terraform, you already have either a default AWS profile or exposed environment variables in the shell. So even if you don't get a permission denied error in this step, I highly recommend following along. Alright, first let's use a naive approach and create IAM user for Terraform, which we rarely use in real environments. Even with IAM users, you never attach IAM policies directly to users. Instead, let's create IAM group Terraform admin. And yes, you can have different permission sets for different users and different workflows. For example, to run a plan, you don't need write access, and so on. We'll cover it in the production project structure section. For now, let's use admin access and attach it to this group. Next, let's create IAM user. You can use any name, you just need to be consistent. Now, let's place this user in the Terraform admin group. And click Create User. We also need to generate static credentials for this user. Click Create Access Key, select Other, and generate access key and secret key. When you're just getting started, most likely you ran AWS configure command and generated a default AWS profile. For this tutorial, we want to create a custom new profile for this new user. Let's copy and paste access key, then the secret key, and don't worry, I'll immediately delete this user right after I finish recording this tutorial. Now we can quickly verify that we can use our new profile. All the commands are available on my website, so you can just copy them from there. If you can get user details from AWS, it means it works. We'll be frequently testing in order to discover any issues as early as possible. It will help you to debug in case something went wrong early. When you're not using a profile in the provider definition, it will use default AWS profile. So now we want to specify our custom profile for my user. Let's give it a shot and try to run Terraform plan one more time. This time you should not get any errors, and you should see seeder range for your default VPC, but it's not yet registered in the Terraform state. But at least we are able to verify that we successfully authorized Terraform with AWS. Most of the time, instead of IAM users with static credentials, you would use IAM roles with temporary credentials. Let's go ahead and create IAM role for Terraform. Again, in real environments, you will have multiple IAM roles with different access. For example, Terraform admin to provision resources, Terraform viewer to run a plan, and so on. And different people would be allowed to use different IAM roles. Let's select AWS account. It's going to be your account number, and click Next. We can use the same admin access IAM policy and this time attach it to the IAM role. Let's call it Terraform admin. And of course, in real world, you would have custom IAM policies that you would attach to your IAM groups and roles. You would never attach admin role to almost anything. Alright, at this point, we have Terraform admin IAM role with full access to AWS account. And this is IRN or Amazon resource name for that IAM role. In your case, you should have the same name, but a different account number. Now, let's verify that our IAM user has access to that IAM role. Specify IRN of the role and profile with your username, and you can use arbitrary name for the session. At this point, we should have permission denied error, but for some reason we can actually assume this role. For the first time it might be confusing, but this happens only because IAM user has admin access, which you would almost never have in real environments. Let me explain how to allow specific users to assume specific IAM roles in your account. Well, let's fix this first. Usually, your Terraform account, instead of admin access policy, would have policies associated with the resources you want to manage using Terraform. So let's remove admin access policy first. And instead, since we only interact with VPC, let's give it a full VPC access instead. Now, our user still has full access to VPC, but it would not be allowed to assume Terraform admin role. Let's verify this first. If you run Terraform one more time, it should still work and you should see VPC seeder. But if you try to assume Terraform admin role, we will fail and get a permission denied error, which is expected and very typical for most AWS accounts if you're not using users with admin permissions. Well, let's fix this and grant our IAM user access to this Terraform admin role. First, we need to create a new IAM policy. Later, we'll convert everything we do using AWS console to Terraform code. Let's select STS for the set of permissions. For the allowed actions, let's select Assume role. For the resource, potentially you can allow assuming all roles, but the best practice is to limit to only the roles you actually need. Let's type Terraform admin, or you can just paste the entire IRN of the role. It's up to you. The more you type, the more chances you might make a typo and something will not work. And later we would use JSON instead of typing everything in the UI. So your role should look like this. The only difference should be your account number. Let's call it Assume Terraform admin role and click Create Policy. The next step is to replace the full VPC access policy with this policy. Let's remove this policy first. Then attach our new policy to this IAM group. To summarize, now your user has only one permission in this AWS account to assume Terraform admin role. By itself, it would not be allowed to do anything. Let's verify that we can assume that role with our IAM user. This time it should work. Let's also try to run Terraform. Well, now my user won't be able to retrieve VPC details. It can only use Terraform admin role. And this time you should have static credentials for the user. And most likely you would have a default profile as well. And you should have maybe a default profile and the profile for the user we created for Terraform. If you were running Terraform from EC2 instance, you don't need this, or from CI/CD tool like GitHub Actions. But to use it locally, you need to create a new AWS profile to use that role. You can use any text editor and add another profile. Copy and paste IRN of the role. And for the source, let's use our new IAM user. So on line 3, we created a new Terraform admin profile that we can use in Terraform. Let's replace it in AWS provider. Finally, let's verify if we get access back and are able to run Terraform. Next, let's run apply, which would not create anything but register VPC seeder output variable in the Terraform state. First, it would run the Terraform plan and you type yes to continue. Potentially, you can skip this step by typing auto approve, but I highly recommend that you never do this. It's very dangerous and might create a lot of problems for you. Just know that it exists and never use it directly. It is only used in CI/CD workflows. For example, when you merge a pull request and Terraform automatically apply the changes, which we'll do in GitHub Actions section. So for now, we have only VPC data source in the Terraform state, which has a seeder block, and also we have output variable registered in the state. Now, let's do something more useful with Terraform. Let's create EC2 instance. This time, instead of data keyword, we use resource. Later, we'll need to find AMI to be used for this EC2 instance. For the instance type, let's use T2 micro and give it a tag. You can use a special name tag which starts with capital N to be visible in AWS console. Also, you typically add environment, maybe owner, and so on. AWS tags are very useful and heavily used by many tools, including EKS. Now, instead of creating a data filter, let's actually find AMI ID in AWS console. Different regions might have different AMIs, so make sure to select the same one your Terraform provider uses. Let's search for Ubuntu and use the first one with LTS, which means long-term support. And we need to copy AMI ID and paste it into Terraform. The next step is to run Terraform plan, which is a safe way to review all the changes that Terraform will make in your account. One of the most important lines, which you always need to review, is the summary. Never proceed if you have more changes than you expect. In our case, we only have one item to create, which is EC2 instance. And this is exactly what we expect. Also, each resource will have action associated with it, like it will be created, updated in place, replaced, or deleted. Only after you carefully review the plan, you can run Terraform apply. You might see a warning and we'll fix it in later sections when we get to CI/CD pipeline with GitHub Actions. For now, just make sure you have exactly the same changes after you run apply and confirm it. It's going to take a few minutes to create EC2 instance. In AWS console, let's confirm that we have EC2 instance and that it used T2 micro instance type. Now, if you want to make changes to your infrastructure, you just need to update parameters in the Terraform code. So let's say we get more traffic and we need to increase EC2 instance type. We only need to replace micro with small type and apply Terraform. In the summary, you can see that one item will be changed. Sometimes when you change the attribute of the object, Terraform won't be able to update it in place, and we'll have to delete and create a new type of that object. So be careful, and we should also review the type of the change Terraform wants to make. Let's refresh the page and verify that Terraform updated the type of the EC2 instance, and now we have the small type. In Terraform State, we should have by now a new EC2 instance item that describes the live state in our AWS account. Well, sometimes when you have a lot of team members who work on the same infrastructure component, you might see some drift in Terraform and the state. Let's say now the traffic to our website went down and we want to reduce the EC2 size to reduce infrastructure cost. Let's revert back to micro. Also, let's say someone on your team made a change to the infrastructure and forgot to commit and push the changes to the remote repository. It's more common than you might think in large companies, and later I'll explain how to avoid such a problem. So now let's say we have another proxy EC2 instance added by someone else and your change for the existing EC2 instance. If you ran the plan right now, obviously Terraform would try to create a new proxy EC2 instance and update your EC2 instance. The proper way would be to contact that person and wait until he or she resolves the drift and commits their changes. But for some reason, if that person is not available right now and you're not able to fix the drift, you can make your changes through the UI, of course, or you can only apply your changes. For that, you can use a target option and specify the resource you only want to modify. This time, Terraform will only target that resource, and you should see only changes related to your work. Also, you might get a warning from Terraform. Let's run apply using target option as well. Make sure Terraform will only modify the single resource and type yes. This kind of situation is very common in large companies without proper Terraform workflows and might be dangerous. And later I'll explain how to avoid them in the first place. Now let's make sure we only have one EC2 instance and it was updated to use the micro instance type. If you just run Terraform plan now, you should only see that a new proxy EC2 instance will be created. And now you have time to resolve this issue. Now, let's say we want to destroy our infrastructure. We can use Terraform destroy, but it's very rarely used and only useful for temporary environments that you create to run some tests. Let me cancel this. The more common approach would be, if you want to remove something, is just to commit it out or delete it entirely from the code. Let's run Terraform apply, and you should see that Terraform will destroy our Ubuntu EC2 instance. Let's confirm and remove it from the AWS account. You might be told that you are only allowed to use Terraform to modify your infrastructure, but it's very common again in large companies or during production incidents to modify infrastructure using AWS console. But later you always must import all the changes to Terraform. So let's create EC2 instance using UI first. Let's give it a name Ubuntu using a capital U. Select exactly the same AMI ID for the EC2 instance. For the EC2 type, I'll on purpose use a different type, small. We don't really need any keys. And finally, select existing default security group. Alright, now we have a single running EC2 instance. The first step to import anything in Terraform is to create corresponding resource in the code. I'll be using the existing one with micro EC2 instance type. Let's see what happens. If you run Terraform now, it will simply try to create another EC2 instance, but that's not what we want. Instead, we want to import this resource. The easiest way is almost always just to Google that resource type. So right now we want to import AWS instance. For any type of resource you want to import, you can scroll all the way down and find example. Different resources will have different ways to import. You can use a declarative approach, but I prefer old way, which is pretty much the same thing. So from this page, you can see that you need EC2 instance ID to import it. Let's run Terraform import and find the resource along with the variable that we want to import. And then we need to find EC2 instance ID from the AWS console. And that's it, you can press enter. You can see that EC2 instance was imported, but it's very common that the actual state will be different from what you actually declared in Terraform. Let's run Terraform to confirm. So now, instead of creating EC2 instance, it will try to modify it. At this point, you need to make a decision if you want to modify it or simply import it. Let's say we want to import, so we need to match Terraform code with the live state in AWS. Let's change the micro instance type to small. If you run Terraform again, you should see no changes required. Another way to import it is declarative approach. You can use import block and provide the same thing here and run apply. Well, since we already imported that EC2 instance, it won't make any difference. Another more or less common thing in large companies is to remove items from the Terraform management. Let's remove or comment out EC2 instance and run Terraform. And as we would expect, Terraform would try to destroy that resource. In order to remove this EC2 instance from the Terraform and not destroy it, we can use Terraform State remove command and specify the resource we want to remove. It's pretty much the same thing as import. You can do the same with modules as well, which I'll show later. So now it was removed from the state, and let's confirm for the last time. Alright, but don't forget to manually delete this EC2 instance from AWS. So this is just a beginning, and in the following sections we'll gradually start to improve our Terraform workflow so that in the end you'll be able to use it for production environments.